cycle of stars. Stars are fundamental to the structure and dynamics of the universe, serving as the primary source of light, energy, and heavy elements, essential for the formation of planets and life. Understanding the life cycle of stars from their birth and stellar nurseries to their spectacular deaths provides profound insights into the evolution of galaxies and the cosmos as a whole. Introduction. Stars are born from vast clouds and gas and dust called nebula. These clouds undergo gravitational collapse, leading to the formation of protostars and eventually stars. Throughout their life, stars undergo various stages of nuclear fusion, where they convert hydrogen into helium and other elements, releasing immense amounts of energy. The fate of a star depends largely on its initial mass, which determines its temperature, luminosity, and eventual demise. 1. Stellar birth, formation of protostars. The process of star formation begins with dense regions of interstellar gas and dust, primarily composed of hydrogen and helium, with traces amounts of heavier elements. Under the influence of gravity, these regions collapse, forming dense cores known as protostars. The collapse is triggered by external disturbances, such as supernova shock wave or gravitational interactions between nearby stars. 1.1 Gravitational collapse in protostellar disk. As a molecular cloud collapses, it forms a spinning disk around the protostar. This protostellar disk plays a crucial role in the acceleration process, where gas and dust from the disk fall onto the protostar surface, gradually increasing its mass. At this stage, the protostar is embedded within its natal cloud, obscured from orbital view by dense dust cloud. 1.2 Protostellar evolution in pre-main sequence phase. During the pre-main sequence phase, the protostar continues to accelerate mass and undergoes contraction and heating. Gravitational energy is converted into thermal energy, raising the temperature of the protostar. As the internal temperature rises, nuclear reactions begin in the core, initiating the next phase of the stellar evolution. Main sequence phase, hydrogen fusion. The main sequence phase is the longest and the most stable period in the star life, characterized by stable nuclear fusion and hydrogen into helium in the star's cores. This phase typically lasts for billions of years, during which the star maintains a stable balance between the inward gravitational force and the outward pressure due to the nuclear fusion. 2.1 Stellar structure and energy transport. In stars like the Sun, nuclear fusion occurs in the core where temperature and pressures are sufficient to overcome the electrostatic repulsion between hydrogen nuclei, protons. The energy generated through fusion is transferred outwards through radiation and convection, depending on the size and composition of the star. 2.2 The Hertzsprung-Russell diagram and stellar classification. Stars are classified based on their luminosity, temperature, and spectral characteristics. The Hertzsprung-Russell HR diagram plots stars according to their luminosity against their surface temperature. Main sequence stars provide a diagonal band on the HR program, with hotter and more luminous stars positioned towards the upper left and cooler left. Luminous stars over towards the lower right. 3. Stellar evolution, post-main sequence. As the star exhausts its core hydrogen fuel, its evolutionary path diverges based on its initial mass. The subsequent phase of stellar evolution depends significantly on the interplay between internal nuclear reactions and the star's outer layers. Red giant phase, hydrogen shell burning. For stars with masses similar to the Sun, about 0.5 times to 8 times the solar masses. The core hydrogen burning phase ends when the hydrogen fuel is depleted. With the core contracting and heating, hydrogen burning continues in the surrounding shell around the inert helium core. This process causes the star outer layer to expand and cool, transforming into a red giant. Helium burning and stellar masses. The more massive, greater than 8 solar masses. Helium fusion commences in the core after the exhaustion of hydrogen. These stars evolve rapidly through subsequent stages, including helium burning in the core, leading to the production of heavier elements, up to iron, via successive stages of nuclear fusion. The outer layer may be expelled into stellar winds, enriching this interstellar medium with newly synthesized elements. Stellar end stages, supernovae, and stellar remnants. The final stages of a starlight depend crucially on its mass. For massive stars, the composition of its nuclear fusion leads to a catastrophic collapse, an explosion known as a supernova, while lower mass stars experience central transformation. 4.1 Supernova explosions in stellar recycling. Supernovae are immensely energetic events that release more energy in a few weeks than the sun will make all over its lifetime. They are responsible for dispersing heavy elements synthesized during stellar lifetime into the surrounding interstellar medium. Supernova remnants, such as the Crab Nebula, observed as expanding shell of gas and dust and rich with elements essential for planet formation and life. 4.2 White dwarfs, neutron stars, and black holes. After a supernova, the remaining core of the star may collapse into a compact object, a white dwarf, neutron star, or black hole. Depending on its initial mass, white dwarf or dense remnants supported by electron degradacy pressure, while neutron stars and black holes represent the extreme endpoints of stellar in evolution, characterized by their high densities and strong gravitational fields. 5. Conclusion. Cosmic significance of stellar life cycles. The life of stars illustrates the interconvergences of celestial phenomena, from the birth of stars in the stellar nurseries to their dramatic deaths as supernovae and the subsequent formation of these new stars and planetary systems. Through their evolution, stars enrich the universe with heavy elements, provide their energy necessary for life, and serve as cosmic laboratories for understanding the fundamental physics processes. Studying the life cycle of stars enhances our understanding of the universe's origins, its current structure, and its future evolution. This underscores the dynamic interplay between gravitational forces, nuclear reaction, and electromagnetic radiation that govern the cosmos on both of the smallest and the largest scales. As technological advancement enable more detailed observations and theoretical models, our comprehension of stellar evolution continues to depend, offering profound insights into the fundamental principles that shape the universe as we know it.